Thank you. Our speaker today is Ross Salawitch. He's a professor at the University of Maryland. I just quickly checked on his bio. Bachelor of Science in Applied Engineering Physics at Cornell, PhD at Harvard in Applied Physics, was at NASA JPL from 94 to 07, joined University of Maryland in chemistry and biochemistry from 07 to the present. And among his awards are the AGU Kaufman Award for Unselfish Cooperation in Research and NASA Exceptional Achievement Medal. And you can see the title of his talk up on your screen, which is Critical Evaluation of Projected Global Warming with an Empirical Model. So Ross, with that, take it away, please.
Thanks very much. I want to begin by thanking the great team of students and as well as Walt and Tim, who are no longer students, who work on this project. We've gotten a number of PhDs out. We have a number more on the way. Not really the best title, actually. I'm going to talk about global warming, and I'm going to talk about what we think really is happening and what we think really will happen in the future. I'm going to begin by reminding people of a very important figure. Oh, and before I go any further, you know, I will certainly be happy to entertain some interruptions and some questions, provided it's not total derailing of the topic. So if people want to do that, I don't know what the norm is at your seminar, if you just speak up or raise your hand or whatever. But Steve, if you want to help me moderate that, I'm fine to have some conversation along the way.
I think it gets a little complicated doing this by the Zoom. Why don't people hold their questions to the end and we'll take it from there. Thanks.
Okay, so I'll try to be expeditious in the time. Okay, so this is a figure from the AR5 report that shows how temperature has changed over time, the temperature anomaly, global mean surface temperature, and results from the CMIP5 models. And this was a fairly astonishing figure at the time, because you would like for the data to lie in the middle of the models, not at the lower edge of the models. And this led the authors of chapter 11, which I had no involvement with, to come up with a trapezoid, which is their indicative likely range of how much global mean surface temperature will really rise over this time period, assuming no future volcanic eruptions. And we will see this trapezoid throughout the presentation today. Please note that it falls around the bottom half of the projections from the CMIP5 climate models. I also want, as part of this introduction, to show a figure from the Karska et al. Paper that came out in Science Advances last year. And without explaining, I know I should explain everything in all my figures, but in the interest of time, I'm not explaining every point in these figures. This is showing projections of mid-century and end-century warming from CMIP6 models, color-coded by their equilibrium climate sensitivities. And the gist of this figure is that if you actually use constraints on how well the models match observed global warming, you get less aggressive warming by the end of century, or 8.5 degree watt per meter squared forcing, 2.6, and a bunch of others in the paper. So this again comes up with the notion that the full ensemble of the CMIP models are warming too quickly. I also want to draw attention to this paper by Hausfather et al., which has gotten a lot of attention in the press and a lot of citations. Again, I'm not going to go through every entry here, but these are basically skill sets of how well the various climate models have compared to observations. And some of you are very familiar with this paper, I'm sure. I just want to point out that despite the fanfare given to this paper, they stopped at AR4. They did not go to CMIP5, which is AR5. And most notably, look at the scores dropping from the second assessment report to AR4. These numbers look great. One is good, but 0.81 to 0.56. Okay, so the devil's in the details. As further part of my introduction, I want to let folks know that there's something called RCMIP, the Reduced Complexity Model Intercomparison Project. We now have 2 papers out. They're both led by Zeb Nicholls, who I was astonished to find out after having very detailed email exchange with him that he was a grad student at the time. He's now Dr. Nicholls. Malte, who folks know, is the second author. We participated in this, and there was an activation energy barrier to get into the RCMIP. Right, Laura? We had to answer a whole lot of questions and do a whole lot of convincing that we had a meaningful approach to be part of this. Here is a figure from the second Nicholls et al. Paper, which shows the rise of surface air temperature as a function of time from various reduced complexity climate models. These are models that don't use full physics to predict global warming. Now, often these models are only going after the rise in the global mean surface temperature anomaly. Sometimes they do more. Some have interactive carbon cycles. We have an interactive ocean. There are various approaches, various things these models do. Now, here are some of the models I'm sure you've heard of. Magic and Oscar is in here. Hector is in here. What's being shown here is the median box and whisker plot. I think they're 25th and 75th, and min and max of the rise in temperature by end of century relative to this time period from all these RCMIPs. Ours is EMGC. We have the largest uncertainty. Now, you might look at this and say, aha, your model warms less than all the others. You're the outlier. But I will explain later why this is. It has to do with how they handled our results. They're using the median of 100,000 simulations, not weighting by aerosol radioforcing. So we don't handle our output the same way they did. The blue lines in the back are the CMIP6 models. And they're again at the upper end of what not just our RC indicates, but everyone else's RC. And here's a similar projection for SSP 8.5. Again, the reduced complexity models lying at the low end of the GCMs. Okay, I did have the good fortune of publishing a book called Paris Climate Agreement Beacon of Hope. It is available online, open access. I'm told that chapter 1 is particularly good for introductory graduate student teaching. It's called Earth's Climate System. This is a figure from chapter 1, and it is showing our attempt to estimate how radioforcing and climate has changed over time and how temperature has changed over time. And you don't have to do much math to see the relationship here. Want to remind people, well, you all know how much we've warmed, but there's something really, really, really important about this. See the uncertainties. The uncertainty in how much temperature has risen, this is HADQ T4. Actually, this uncertainty is probably a little bit smaller than it should be because HADQ T5 is out, and HADQ T5 is really pretty much at the top here. But notice the uncertainty in radioforcing and climate is so large. And so you would think that we can relate how much future warming we're going to have by, we know delta RF and we know delta T, we just do some simple math. It's fairly linear for small perturbations, but the problem is we don't really know what delta RF was. Well, there's uncertainty with that. And the uncertainty is due to aerosols. So another figure from chapter 1 of our book, this is the greenhouse gas forcing as a function of time for RCP 4.5, CO2 rising, methane N2O, and we put on the bottom of this figure the 71 plausible scenarios for how tropospheric aerosols offset global warming. This is from the Smith and Bond papers, Steve Smith, Tammy Bond. And, well, first off, the radioforcing of tropospheric, oh God, I don't have. This is obviously delta RF and what's per meter squared. Okay, so this is going away because of public health. Climate be darned. So if we live in this world where aerosols have offset a lot of global warming, we're going to unleash a lot of greenhouse gas warming that's been hidden. And if we live in this world, which I would say from the climate change perspective, we hope we live in, aerosols have not offset that much. We're not going to unmask a lot. But look at this wide range here. That's really critical to what I'm going to show next. I'm still in the introduction. Okay, so I'm going through these figures quickly because you all know this stuff in these figures. Okay, this is our version of AR5 delta radiaforcing 1750 to 2011. The best estimate of how much warming was offset by aerosols is -0.9 1/m². Steve has written extensively on this. Plays a large role in our understanding of all this. Here's the likely range. Okay, so check out AR6. Oops. Okay, AR6. So AR6 has a larger number, later year, a large change in the indirect effect versus the direct effect. This is all pretty much due to one paper by Chris Smith et al. How exactly they did this, I'm not really sure. But we went from the AR5 best estimate. God, I can't believe I look at this and don't see my y-axis, watt/m² radiaforcing. All right, they went from this line to this line. That's so weird and so hidden in the details. That's really weird. Maybe it's well justified. I hope we don't really live in this world, because we're in a world of hurt. We're in a lot of hurt if we do live in this world. Nearly everything I'm going to show is, or everything I'm going to show is based on AR5 best estimate, because that was what was out at the time our paper was written. So this is what we do. This is one of the equations that guides our radiative, our empirical model of global climate. Rather, we do have more equations. We're not just one equation, but this is our primary equation that guides how the global mean surface temperature anomaly, cosine weighted by latitude, sea surface air, how that changes as a function of time, driven by greenhouse gas radiaforcing, aerosol radiaforcing, land use change, and we also consider natural forcings, stratospheric aerosol optical depth, total solar radiance, and so, etc. The one thing we do different than most regression, or one of the two things we do different than most regression approaches, is we actually use AMOC, Atlantic meridional overturning circulation in our approach. Everything I'm going to show you, the scientific results will be unchanged if we don't use AMOC. The big effect of AMOC is a somewhat noticeable reduction in how much volcanic cooling we infer in the record. And that's what we wrote about in our first paper, Canty et al., 2012, I think, almost a decade ago now. The other thing we do different is we actually watch heat in the system and quantify it. So we have an interactive ocean, and so we take track of how much temperature is perturbing the system, how much radiaforcing, how temperature responds, and heat flow into the oceans. And you can read McBride et al. For further details. So here's just our roadmap here. I'm not going to leave this on screen for long. We solve for climate feedback, and there are various ways we could define climate feedback. We're consistent with the Boney et al. Framework. We solve for ocean eddy diffusion. We do have a 6-year lag that I'm not showing here that's built into our representation of flow of energy into the ocean. That comes from a paper that Steve led. And so we basically solve for climate feedback and ocean heat uptake. The red line here is the result of our model. The black line is had crew T5. This is the human component to global warming. I'm going to talk a lot about this. Here's the solar component in purple and the stratospheric aerosol optical depth, volcanoes in blue, and so AMOC, which we use a filter to pull out the long periodicity here. And most importantly, we're constraining to measured ocean heat content, a very important aspect of our work. Okay, now input to our model are the SSPs. If you have questions about SSPs, Laura McBride is on and can answer them. She's the lead of this paper. She recently defended her PhD. Here's CO2 going up. methane going up and 2O at various ways for the SSPs. We're going to, point to SSP 3.4 and 2.6 as being pretty favorable for trying to attain the Paris Climate Agreement. We have to turn over CO2 really quickly, and we have to somehow arrest the growth of methane, or maybe even pop it down, despite what the data are doing. Nobody pretends that we can stop the growth of nitrous oxide because it's so endemic in agriculture. We also constrain to ocean heat content, and look, we hear the criticism of our work, and we hear it in paper reviews, proposal reviews, and EGU and AGU sessions. So you only have one equation. Actually, we have one equation. Our response to the criticism is that our approach uses millions of independent data points, not hundreds, not thousands, but millions and millions. And we do a detailed, rigorous error analysis that you can read about in our paper. The abstract, the supplement is like 60 some pages long. The paper itself is pretty substantive, but we have a huge supplement going into how we handle the error analysis. This is the record of ocean heat content we use from 5 different papers. Some of these are dependent, most of these are independent. They use various techniques. Obviously, the closer we are in time, the better we know ocean heat content from some of the oceanographic programs. The estimate for the uncertainty that we use pretty much comes from Cheng et al. With some slight modification that you can read about. This is a model of it. The other thing that we do differently, and we think is vitally important, is how exactly we handle aerosol radioforcing. In our earlier work, we came up with our own in-house schemes for aerosol radioforcing that looked at 6 different types of aerosols, 3 that cool, 3 that heat. For the latest version of our work, we're scaling the curves that CMIP6 gives us. The dang on problem is they only give us 1 curve for each SSP, 1 curve. Yet we know that this is highly uncertain. So we use constant multiplicative factors to scale the aerosol radioforcing. These curves are slightly different for the various SSPs. We scale these to sample the phase space of the climate system for what Smith and Bond told us. Now, we're not using their scenarios exactly in this paper, but we could have. We actually made an executive level decision that we had a better chance of getting our paper accepted if we stuck to the CMIP6 specification of aerosols than if we had used Smith and Bond, even though we may have preferred to use Smith and Bond, because we think Smith and Bond more rigorously cover the phase space. And for those who know this is the rapid rise of coal, right? And then scrubbing of coal that's causing all these changes. But is it offset a lot by black carbon, or is it not offset by black carbon? Okay, so here's the problem we face. Here are 3 model simulations. The only thing that's different in these model simulations is how we handle aerosol radioforcing. They're all based on SSP 3.4, that's CO2 leveling off and methane leveling off. If we assume that aerosols have offset very little of the global warming, then we fit the climate record with a rather modest climate feedback. And if we make an assumption that whatever feedback we need to fit the past perpetuates into the future, and I'll talk about the validity of that assumption at the end, if we assume that, then we actually will achieve 1.5 degree warming by end of century. That's what this bottom gold is, if we can place greenhouse gases on SSP 3.4. Good. The problem is this is not AR5's best estimate of aerosol radioforcing. This is. Okay, we run the simulation for that case. We need stronger climate feedback to fit the climate record. Here's reduced chi-squared over the last 40 years. I'll explain this in the next slide or 2, what this means. These are equally good simulations. Now we're hitting 2 degrees warming. Okay, if actually we could limit warming to 2 degrees by end of century, even though we want 1.5, if we can achieve 2, I think that would be called a win. The dang problem is that if This aggressive masking of climate by aerosols is the world we live in. And I sincerely hope it's not the world we live in. If that's the world we live in, then we're going to have a whole lot of future warming as we clean up the aerosol precursors for public health concern, because we need much stronger climate feedback. This is an application of radiative forcing by greenhouse gases of more than a factor of 3, a little bit more than a factor of 3 by clouds, albedo, water vapor lapse rate, you name it. Okay, and this is basically clouds doing nothing. So this is just the water vapor lapse rate value, but we get this independently, and this is clouds being moderately positive. Okay, so the first thing I'm going to talk about in our results is something we call attributable anthropogenic warming rate. I've rearranged the equation slightly. I've placed the Q ocean term up here because we're assuming before humans got involved, Q ocean was 0. Of course, I know about ice ages and glacials. I know the climate system changes, but over the 2 millennium before humans got involved, we were pretty quiescent. So the slope of this term is indicated on this figure here. So we say humans have led to about 0.17 degree per decade warming. This is just the uncertainty that these scores fit, which isn't the real uncertainty. We base our work on Foster and Ramsdorf's, highly cited paper, but we extend to 2014 rather than 2010 because the CMIP6 runs that we want to look at, the historical runs, stop in 2014. So this is a really important figure from our paper. This paper shows the results of aawr, attributable anthropogenic warming rate, found for all simulations that we can best fit the climate record. I'm sorry, my slides are a little bit out of the order I thought they were. I haven't explained what these reduced chi-square terms are. This is coming pretty soon. So just remember, we have 3 reduced chi-squares less than or equal to 2. Now, most of the work in our paper is based on HADQ-T5, which is the most aggressive warming. It's because they use the count and weigh suggestions or how to handle the closing of stations in the Arctic to better fill in the Arctic. So HADQ-T4 warms faster than HADQ-T5 warms more than HADQ-T4. Our paper was submitted and ready to go with HADQ-T4. And if so, it would have met the ipcc deadline. The dang on reviewer insisted we redo everything, right, Laura, for HADQ-T5. Really? Like every single figure? Our paper is much better and more time relevant, but it missed the ipcc deadline, sadly, for us. I do not know why the Japanese data warms much less. I don't know what they're doing differently. Here, the different box and whiskers are the 5 data sets for ocean heat content, showing a pretty small effect. The primary driver of the uncertainty here is lack of knowledge of aerosol radioforcing. So that even impacts how much climate warming we attribute to humans, because the shape of the aerosol radioforcing curve begins to differ from the shape of the greenhouse gas, right? The greenhouse gas curve rises over time monotonically. The aerosol curve turns over around 2000. So how you combine those shapes is really responsible for this. Okay, here's my partners. Okay, here they are. Okay, so we have 3 goodness to fit partners. We're kind of inventing the science ourselves. One is how well we fit the ocean climate record. Another is how well we fit, we say recent, it's the last 80 years, I guess. I incorrectly stated this earlier. It's from 1940 to present. It's a time where climate's warmed. And then the whole time period. Now, in our earlier work, we had only focused on the whole time period. But this became untenable when we added an interactive ocean to our model. We got solutions in here that we didn't think were realistic. They satisfied reduced chi-squared over the whole time period, but they diverged significantly from the climate record over the time period that we really care about in a way that we thought we had better add another constraint. So what I'm showing here is the variation of aawr, this slope of that line, as a function of a single quantity, how much aerosols have offset global warming in 1 year, 2011. Now, of course, in the model, we have a time series. This is the value of the time series in 2011. If we've, have aggressive masking, we say that there's been more human-induced warming, less aggressive, lower. This, we call it an ellipse. It's not really an ellipse, whatever this shape is the range of model space where we can get reduced chi-squared less than or equal to 2 for all 3 parameters. Now, what we like to do, is we like to fit our results by how likely any value of this aerosol radioforcing is. So IPCC 2013 AR5 said the most likely value was -0.9. And here's basically we fit a slightly asymmetric Gaussian because their values are slightly asymmetric. And basically we average the data for this value. This is like 100,000 simulations. We average in each value of our curve and we weight it by the height of this slope. And the reason we do that is that if we didn't do that, we would unduly bias our results low. If we just did a grand average, because see, we don't have many points up here because the model phase space tightens. And this is what we used to do early in the game. And we realized that that was flawed. But this is what Nicholls et al. Insisted they do. So they just use the grand median so that they bias our results low. It's all good. We say come to our paper for our real results. So we weight by how likely it is that aerosol radioforcing occurs. And note, we can't even achieve fits to the climate record for some of these aggressive scenarios. So the climate record, we say in our approach at least, which you can, I'm sure, shoot lots of darts at, we don't have a fit to the observed rise in global mean surface temperature. Okay. Next, I'm going to show you what aawr is from the climate models. I'm going to do this 2 ways. I'm going to take, in this case, I'm showing CMIP5 results because Laura, I couldn't find the figure for CMIP6, so we'll get this in our talk soon. CMIP5 results, and we just omit from the fit data acquired during prior to the time we care about. So we're starting in 79. So if it's omitted, it's in light blue. We omit Elchi-Chon and Pinatubo, and we just do a least squares linear fit. That's the poor man's way of doing this. We could do better. We can run regressions on the CMIP6 results, and we can regress out what volcanic cooling does, because this is historical runs that used SAOD. So we can pull that out. Of course, the ENSOs, the AMOCs, they're all random in these models. And TSI, very hard to see a solar radiance signal in the CMIP6 output. It's in for some of the models and not others. Okay, this is AAWR, attributable anthropogenic warming rate from the CMIP models, linear versus regression. I will never lose sleep over a 1% difference. They're the same. It looks like it's biased high. If it's biased high by 1%, you all can argue about that. I'll leave the room. This is the result I want to draw attention to. The median value of attributable anthropogenic warming that we infer from 50 CMIP6 models, the median value is higher than the upper limit that we infer from the climate record. If you're going to base policy on the CMIP5 or CMIP6 models, what I just said should really cause you to pause. And that's why the Tokarska et al. Paper got into Science. Because, they realized this and said, look, we better place the models in a framework of reality. Now, you might think I'm obnoxious and arrogant and might tell me so when we get to the questions and answer session. These GCMs are vitally important. We don't pretend to come anywhere close to the societal relevance of these GCMs. They tell us how sea ice will change. They tell us how precipitation will change. They tell us how growing season will change. They tell us so many vitally important aspects of the climate system that we need to know for policy. What we're saying is maybe what you ought to do is realize that the climate models warm too quickly, and it's probably due to too positive cloud feedback, particularly mid-latitude, low altitude clouds. Mid-latitude, low altitude clouds, Zelinka et al., Zelinka et al., ON, Zelinka et al. That's probably what's going on with the models. What we would say is maybe you can use the reduced complexity models to say how much will warm by a certain time, then go into the GCMs and find they're warming, 1.3 degree warming, and say, okay, what happens when you warm by 1.3? How's the fire season change? So this is synergistic or complementary to the GCMs. We're not arguing that the GCMs aren't useful. They're incredibly vitally important and useful. What we're saying is there might be a better way to look at the output of the GCMs. Same story with ECS. ECS, equilibrium climate sensitivity. I'm not a fan of the ECS. I'm not a fan of the Gregory method and how it's calculated. Why? Because it's for 4 times CO2. And then they just take the result and they divide it by 2. But the delta RF for 4 times CO2 is not twice the delta RF of 2 times CO2, but that's what they do. And that's what we did. And Laura can talk ad nauseum about this if folks did want to talk about it. We talk about ECS. Why? Because we have to. Okay. A very important paper of Laura, a figure of Laura's paper that really should have been in Maine, but we produced this figure based on the great review. If any of our reviewers are here, thank you. The great reviews we had. This is a plot of ECS versus aawr from all of the CMIP6 GCMs. And we name the CMIP6 GCMs that fall within the range of our best estimate of what ECS is truly from our empirical model. So that's this asterisk for ECS. The red is us, and the circles are GCMs. And our best estimate of the lower limit, and upper limit of aawr. And there are 2, 4. Some of these are cousin models. There's 6 different submissions from 1, 2, 3, 4, 5 independent groups that fall within the range of what we infer the truth to be. So we're not saying that all of the GCMs warm too quickly. We're saying most of them do. Okay, speaking of which, this is moving more to our projections of the future. So this is another important figure from our paper. This is looking simply at all of the CMIP6 GCMs that had submitted at the time we prepared our paper and for different SSPs. This is the ipcc 2013 trapezoid. Oh, this trapezoid has really been our best friend for, and this trapezoid, I'm actually astonished survived peer review because it was total back of the envelope. You can't understand from reading chapter 11, which we've read multiple times, how exactly they came up with this trapezoid. And no one can tell us. It was just, and we've asked, it was their best guess estimate of what reality would be given the conundrum they faced at the time when they were writing the 2013 reports, and this was in 2010 or 11, that the model seemed to be warming too quickly. Yet, same situation. So what we do is we compute how much warming we'll get as a function of time, which I will soon show you. But now I'm plotting warming at end of century in units of degrees C, the change in the global mean surface temperature cosine weighted anomaly relative to pre-industrial for 4 different SSPs. And this is, again, the model phase space for which we can achieve reduced chi-squareds less than 2 for our 3 fitting parameters. And what we do in our world is we, again, weight by the likelihood, according to the experts, that any specific aerosol trajectory is the truthful one. We really don't know this. We wish we knew this better. Oh, do we wish we knew this better? If we didn't weight this way and we just did a multi RCMIP or our RCMIP is EMGC, empirical model of global climate. If we did a multi-model mean we would bias our results low relative to this way. We think we don't care about what our results are. We just want them to be the best we can give the community. This is what we think is the best we can give the community. So we come up with this plot. If we have any New Englanders here, they'll like what we name all of our plots. We call this the Patriots Plot because it's red, white, and blue. It helps us to give names of our plots. What do we show? We're showing the probability that warming will be a certain amount as a function of time. So we will warm at least this much. We have a certainty, probability of 1. We have no probability that we'll warm higher than where my cursor is. So this is the most warming we expect to get. This is for SSP2 4.5. This is the most warming we expect to get. Here's the Paris 1.5 and 2. Our median value or our best estimate is in white. Here's the CMIP6 multi-model mean, right around our upper limit. Here's the CMIP6 max, which diverges wildly from the data from a climate perspective. This is a wild divergence, okay? Here's the CMIP6 multi-model min, which is right around our best estimate. And aha, here's our best friend, the ipcc trapezoid. So we, if nothing else, have given scientific rigor to this trapezoid. Here's the CO2 trajectory associated with this figure. And we say that we have no chance of achieving 1.5 warming if we follow this trajectory, and we have 33% chance of keeping below 2 degrees. If we have more aggressive reduction of CO2, we begin to have a 2/3 chance of keeping warming below 2 degrees. The CMIP6 models wouldn't say that. And we have a 20% chance of keeping 1.5 degrees. And, you know, we can generate these plots in a day. You could not sample the aerosol radioforcing phase space in the GCMs in a comparable manner in less than, Steve shaking his head, I can see you, Steve, you know, years, many years. Maybe you can use some AI to speed these up. So this is complementary to the very important GCMs. SSP1 2.6, okay, now we're getting pretty good at 2 degrees, 50-50 at 1.5. The astonishing part of our result, and I think what convinced Nicholls and Multi-Meinhausen to actually let us into RCMIP, is that even for SSP1 1.9, 1.9, we still can't guarantee that you'll stay below 1.5 degrees. There's parts of the climate system that we can pull out that we go above a considerable part of the climate system. Okay, I'm not worried about this 98%. I'm talking about this 81%. So here's 1.5. I mean, there's 20% of our simulations go above 1.5 warming. That's really crazy. That's crazy. So we have to make policy in light of these great uncertainties. And, you know, those are the worlds where greenhouse gas aerosols have masked a huge amount of greenhouse gas warming. Okay, so here's histograms showing the probability of achieving the probability the temperature will rise by a certain amount. So here's delta T. This is comparing our own projections to that of the CMIP models. You already got the message. We warm less aggressively. We think there's a better chance of achieving the Paris climate goals. Okay, let's talk about some criticisms of it. You've linearized the system. Okay, we have. You know why? The watt per meter squared radiative forcing is 1% on top of 333. I could have used the Miller-Stevens. I don't want to argue about what this number is. It's 1%. Even complex nonlinear systems behave linearly for small perturbations. They do. The more serious criticism. You assume climate feedback is constant over time. Okay, and our reviewers pointed that out. So here's one of our figures with constant climate feedback over time. Let me unveil. These 3 papers provide a view of how much climate feedback has risen over time. The best estimate is about a 50% rise. This is our best fit for the climate record, assuming constant feedback. this is terrible that I haven't written which. No, I do have SSP. This is SSP 24.5. I didn't see this at first. All right, so the end of century warming for this run is here where my cursor is. So we use this black dot to mark that. So we get more warming if we assume climate feedback changes over time. And this is probably the range that I think is reasonable of how much wiggle room we have. But just for illustrative purposes, so here's the values of reduced chi-squared. So this gives us a reduced chi-squared of 1.4 for the recent climate record. We're like, how much can we actually allow climate feedback to rise over time and still keep this reduced chi-squared less than 2? Well, it can change a lot. This is a dang on problem. If we have time-dependent climate feedback, all bets are off. And if I say, how much can climate feedback change and have this reduced chi-squared be less than or equal to 2? I mean, we're through the roof. So yeah, we do assume that whatever happened in the past persists in the future. This is what we think the real uncertainty to that is, but maybe it's higher. Okay, we do compute how much carbon emissions we have left in the system to have a 66% chance of limiting global warming to 1.5 degrees. We had better steeply reduce reductions of carbon soon if we want to achieve this goal. Here is 66% chance of limiting global warming to 2 degrees. And you could, these figures are actually not in our paper. Maybe we should get a second paper out, Laura, getting these figures in the literature soon. But the underlying details of these figures is in our paper, including tables. I thought figures were more attractive than tables, which is why I'm showing these. So again, we're not global warming deniers, which I have been called publicly for our work. I really have been. I really have been. We better reduce really, really quickly. Okay. Now, a paper came out in Science late last year, forecasting what the NDCs, the nationally determined contributions to reducing greenhouse gas emissions, will do to global emissions of CO2. Many of you probably know this paper. I'm going to focus on two of the scenarios. Scenario 3, current policy, continued ambition. Then the updated pledges, continued ambition. And we talk about this in our book, Paris Climate Agreement, Beacon of Hope, that we must continue to decarbonize the economy beyond the stop period of the NDC pledges. We must. So what Cowan O'Keefe has done together with Andy Farago is they've put the emission reductions into GCAM. And what I'm showing here is CO2 as a function of time for SSP 3.7.0 and SSP 1.2.6. So these are two SSPs. And this is scenario CO2 that we compute using GCAM from scenario 3 of the OU et al. I don't know, the OU et al. Paper. And this is scenario 4. So we're straddling SSP 1.2.6, which would, if we can achieve this, and look, we can go on and on about whether we can achieve this, but this is what's the promises that are out there. What I want to draw your attention to is this plot. Here's SSP 3.7.0 for methane. Here's SSP 1.2.6 for methane. And here's what the current NDCs, as best we can tell, from taking the NDCs, grinding them through GCAM, this is where this place is met. So what do? I don't think I put my blend, yeah. So we come up, it's in my backup material. So what we can do with our modeling approach, because it's so simple, is we can come up with methane scenarios that are neither 2.6 or 3.4, but they're blends. They're not, okay, sorry, my bad. Let me go to this. Look, there's a huge range of methane. We create linear combinations by weighting, giving different weights to these two scenarios. So we do a phase space that spans here to here to here to here. I have a backup slide that shows this. We call these the blended methane scenarios. And we can match one of the blended methane scenarios with CO2, N2O, halogens, tropospheric ozone, everything else from one of the SSPs. So in other words, we could do the partial derivative of delta T with respect to methane. Okay, so this is how it looks. So this is what the probability of achieving 2 degrees warming would be for SSP 2.6. Okay, pretty good probability, but if you relax methane, your probability goes down. So if you allow methane to run amok. Now I'm drawing attention to SSP 2.6 because CO2 in scenario 4 lies close to that. The problem is that the methane that we infer from our analysis of the material and the supplementing material, the OU et al. Paper, methane is here. So methane compromises our ability to achieve the goals of warming. If we can reduce methane, these arrows reduce methane, right? Reduce methane, we get higher chances of limiting global warming. Now, the good news from this is the pledge, right? Those who follow this realize that maybe the most important aspect to come out of COP26 was the global methane pledge, which the US adhered to. So that's the good news. I think you all know the bad news. The bad news is what NOAA is finding. The continual rise in methane as a function of time. And we can again have long talks about why methane is doing this. Here's a figure from our book. I'm being given good feedback on chapter 1 of our book, in particular, the Earth's climate system. This shows the sources and sinks of methane and the various contributions from different aspects. The best understanding we get from NOAA of what's driving the methane trends, it's really complicated. It appears to be tropical wetlands. If it's tropical wetlands, our figure has that under natural. It could be a misnomer, because as you all know, as the global climate system warms, the hydrological cycle intensifies. Wet get wetter, dry gets drier. As you all probably also know, what we really observe is the tropics expand. So if it's really coming out of tropical wetlands and it's due to intensification of the hydrological cycle or expansion of the tropics, maybe there's an anthropogenic component to the rising methane. Obviously, landfills, obviously leaking infrastructure of aging cities like my hometown of Baltimore and DC. We fly airplanes around, we measure this, we monitor this, we try to improve this. Obviously, that's very important. Obviously, stopping leakage of methane during the extraction and distribution. But, you know, at the end of the day, we have to get off of methane. I just want to let folks know that a paper appeared last week. Oh man, I didn't put the date in here. This was, I think, April 13th. This just came out. Malti led it. Zeb is a co-author of it. They basically say the same thing I just said. Realization of Paris Climate Agreement pledges may limit warming just below 2 degrees. So we're not on an island. This is what some very famous or well-known people, I'm not into the fame thing, some very highly cited people in the field are saying the same thing. With that, I am at the end. I did go this particularly fast, so we could have some time for conversation, perhaps. No. I think that this is true, that many GCMs, not all, warm demonstrably faster than the actual climate system. Okay, oops, I screwed up my conclusions. This A and B should be under 1 and not 2. Okay, let me explain A and B. We either have some good news here, that the cloud feedback, particularly low altitude, middle altitude clouds, as pointed out by numerous papers, including Mark Zelenka's work. Maybe they're too positive, and Clark Weaver's done work on this, and we have a student who's doing work on this. Maybe this is good news, or it might be bad news. Maybe there's something in the climate system that's idiosyncratic. That's what some have claimed. I went to a really amazing talk a few weeks ago by someone at University of Washington talking about marine clouds and how the sulfur mix in ships has changed over time. If this is really anthropogenic and it's sulfate in bunker fuel and it's going to go away, this is really bad news. So we don't know whether it's good news or bad news, honestly. We do know that the pledges in place put us close to the SSP 3.4 pathway, or 2.6, 3.4, they're about the same. We need to get our focus on methane. And if we actually knew what aerosol radioforcing truly was, and we say this in the decadal survey that I was part of, or if we could really quantify climate feedback, and obviously clouds are a big part of this, and we said this in the decadal survey, and there's this new upcoming mission from CSU that was recently announced, then we could reduce the uncertainties in our forecast. With that, I will stop and be happy to take questions.
Okay, thank you for that. I guess I will ask people to use the raise hand button, and I'm kind of hopeful that when you do the raise hand button, you'll rise to the top of the view gallery. I'm not real expert in this, but let's see if anybody wants to raise their hand. Edmund, I see you raised to the top of the view gallery, so why don't you go ahead with your question? And it sounds like you may be good.
Yeah, so thanks for a great talk. So I think I have a few questions, but one of the questions that you kind of showed that among the CMIP6 model, there are 8 models that kind of agree with the range that you think that your analysis have on fitting the sort of past climate sensitivity and realizable warming. So have you tried to just compositing those models and see whether, or just looking at those models, future prediction to see whether they are qualitatively consistent with your model predictions?
Great question. We have, and it is tricky. Some of the models are, some of the models are not. So some of the models kind of agree with the climate system and then sort of super warm later, and others don't. We've also begun, so I'm going to go a little bit beyond your question if I can. We've also tried to understand why those models behave the way they behave. And we agree with the Zelink et al. Result. This is the work of an undergraduate, Lauren Borgio, which we hope to get submitted. Clark Weaver is involved with this. The trends in the reflectivity of clouds in the models that exhibit high ECS, they're demonstrably lowering the albedo of clouds in the 45 to 45 South region, much more than Clark Weaver says has happened from 1979 to present. So we do see that clouds are part of this. We tried to go down that route that you suggested, and we just said, you know, this looks like a dead end to us, but that's what Tokarska et al. Did. I think that to really answer your question right, you have to look at more metrics in the model than just global mean surface temperature. So Tokarska et al. Have a more sophisticated approach to do this than we had been able to do ourselves. Their paper came out as we're finishing our paper. So we're like, okay, they did this. So they did this, and we are not presently situated to do it better than them.
Yeah, okay. Thank you. Sultan, I see you got your hand up.
Yeah, so thank you, Ross, for a very interesting and thoughtful presentation. So I have 2 very short questions. One is that, so I see that you have AMOC in your regression model. So how did you parameterize AMOC going back all those years?
Good. Laura, can you unmute to help me if I get this wrong? Laura, can you say hi?
Yeah, I can. Yeah, I'm here.
Okay, so we use the Hadley Center SST, and we draw a box. Laura, do you remember the coordinates of the box?
I want to say it's equator to 60 north.
Yep, and so it's
in the Atlantic.
It's that part of the Atlantic. So we look at the SST anomaly. Now, we don't stop there. What we do is we drew a line in the sand. We do not allow a trend for that. So we detrend it, and we detrend it, and we talk about this in detail in the Canty et al. Paper. We detrended by basically using a function that describes how radioforcing and climate has changed over time to detrend that signal. So basically we're looking at ups and downs of the HAD SST record over time. And now there's a lot of high frequency noise in there, or maybe it's signal. So then we Fourier filter it, and we used a 1 over a 9-year frequency fitting of, we basically pull out the decadal time series from the SST anomalies. Now, again, this really mattered extensively for how much aerosol, how much volcanic cooling we get, because during 3 of the 4 major volcanic eruptions over the climate record, we were in an AMOC, in a phase of the AMOC that led to cooling. So basically, the signal of AMOC is not orthogonal to SAOD. Some people have argued that the volcanic signal introduces changes in AMOC, and we discussed this in the Canty et al. Paper. AMOC's leading SAOD. And come on, AMOC's the dog, and volcanic aerosol are the tail. So if we remove AMOC from our results, the one thing that changes is our reduced chi-squared values go up. We don't fit the climate record as well. So there's some structure in the climate record that we attribute to SST. Everything else stays about the same. Our ECS values are about the same. Our AAWR is about the same. Our projections are about the same. So we can live without AMOC. We leave it in because we think it's meaningful to leave it in, but it doesn't drive our primary result that I showed today off course.
Yeah, so the way I understood it, it is the variations in the Atlantic from tropics to 60 degrees that you take as representations of AMOC, right?
Right, and just SST.
Yeah, I understand. So my second question is about, I could see that you emphasize the uncertainty in what will happen to methane. So is there a way of like figuring out about how much, what are the chances that all the methane hydrates lying in the upper layers of the ocean somewhere in the Arctic, they are going to evaporate and add this huge amount of methane in the atmosphere that Thomas Gold had predicted 50 years ago. I mean, how do you, do you account for any of that, or do you leave it aside?
Great. I tend to give long answers to questions. That's a really great question. We only run our model with prescribed methane. We don't have an interactive methane in our model. So the short answer is we don't model that, but let me go further. The best understanding of the methane signal, first off, the explanation of why methane leveled off and why methane started to ramp up. There's so many explanations: number of livestock, natural gas infrastructure, the boom in fracking, wetlands, Arctic. The best evidence that we seem to get is from the NOAA network, which has the spatial patterns. And they say the tropic leads. So if you go to a methane session at AGU or EGU, they say the tropics lead. And so they say it's coming from wetlands. So that means that this time bomb in the Arctic hasn't exploded yet. I'm going to go a little further with your question. And I have to credit Callan O'Keefe, a grad student in public policy at University of Maryland, for solidifying this in my mind. So it turns out that we would say that the climate system isn't warming as fast as most of the GCMs indicate. And Callan O'Keefe reminds me that I had better tell people that you know what's happening? The consequences of climate change seem to be happening in the real world faster than the climate models indicate. How can that be? Well, it looks like that whole Arctic circulation system is going away. The tropospheric Arctic polar vortex, Arctic amplification of warming, it's going away at a prodigiously fast rate, faster than faster than the majority of the climate models indicated. The great Berkeley Earth work showing this amazing Arctic amplification. So, we had better put the brakes on our release of greenhouse gases. Still, we say, still, it looks like Arctic amplification of warming is really happening. If we're going to have release of methane from permafrost or ocean hydrates, that's going to be quite the time bomb. And we're trying to get after that ourselves at University of Maryland in collaboration with James Farquhar by using the rare isotopomers of methane to try to do complementary source attribution to the data. And this project is just getting started. So great question.
Thank you so much, Ross.
Okay, Ping, I think you're next.
Yes, thank you very much. Thank you, Russ, for the wonderful talk. I have a question about these models which showed faster warming. I understand that the historical run usually started from 1850, about 150 years ago, over than that. But I'm wondering, since when, after the time, which year, if there is any, or some decades, then these models demonstrate faster warming, starting from the very beginning, such as, or like 1900, I'm just saying.
Sure. In our paper, we have, I didn't put this in my backup material, maybe I should have. In our paper, we look at how aawr varies as a function of start year and end year. Reasonable start years, reasonable end years. The models, our result of the model warming too quickly basically goes all the way back to the 1960s or so, when the anthropogenic signal really started to be apparent in both the climate record and in data. So, you know, the models just run greenhouse gas radiative forcing and aerosol radioforcing and interactive ocean, some with interactive, they just run and go forward. And they basically begin to lose track of the data starting around 60s and 70s, but they really lose track of the data. So in other words, diverge from the observed global mean surface temperature anomaly around year 2000. So I don't know if that's a really good answer. Now, the further back in time you go, you get, it becomes very complicated to even define what the pre-industrial temperature is, because the uncertainty in the data grow a lot. And we talk about this in our paper. One of the things that we like to do is put all of the 5 or 6 data records, right? HADCU T4, 5, NOAA, NIS, JMA. We like to normalize them to the same time period of the last 20 years. And when you do that, you see these large differences back the beginning of the century. So people's interpretation of the sparse SST data, different groups are quite different. So it becomes hard to really answer your question, but it's mainly over the last 5 or 6 decades that we see it.
Sounds great, thank you.
Okay, Levi, I think you're next.
Hello, thank you for the talk. It's quite interesting. If I'm understanding you correctly, the idea here is that the global climate models are warming quite a bit more than the observations and quite a bit more than what you've inferred with the simple model MIP project, and that a likely culprit would be an overly positive cloud feedback. This probably was in your slides, but I missed it. What cloud feedback would you infer from your work is approximately in line with what we observe in terms of warming?
Great. I have to go all the way back. I know this is a little uncomfortable to watch me do this, and I know there's a way I could go to this. I don't know the slide number. Here it is. Okay. So for those who know the field, and I should have probably put this on here, that's a really hard question to answer because it depends on what we assume about aerosol radioforcing. If aerosol radioforcing really is minus 0.9 mark per meter squared in year 2011, IPCC best estimate, then what this, if we assume the best knowledge we have of the combined water vapor cloud feedback, and Steve knows these numbers, this basically, this number of lambda sub sigma means that the clouds are amplifying the greenhouse gas signal by about 50%. Clouds are moderately positive over time. And I don't think anyone would argue against that based on, series data. There's a link at all papers. Do not say the cloud feedback is 0. They say it's positive. So this is our best estimate. Now, if aerosols have not masked much global warming, our best fit to the climate record is with this value of sigma, of lambda sub sigma. This means that clouds are doing nothing. There's no feedback, there's no change. This is consistent with only water vapor lapse rate. This really large number is consistent with clouds going crazy because we've offset a huge amount. I can go back to this slide here. You know, that value is the radioforcing being really low here, because where's my Smith and Bond slide? I know this is bad to do this. So that's with, you know, a huge offset here. In that case, clouds have to be strongly positive. So your question was, what do we think we can infer from the climate record? We could give you almost anything you want.
I'm more asking you, based on your experience and expertise, based on this work, your best guess if you were forced, uncomfortably forced to come up with a number that you would expect to be more realistic than what the GCMs are pulling.
Okay.
Sounds like maybe the middle figure of something like 1.6 watts per meter squared or something like that, right? It seems to you to be realistic.
I'm gonna go on a limb because we're recording. So I'll probably never be invited to join IPCC based on what I'm gonna say next, but I probably wasn't gonna be invited anyway. I'm stunned that the bonded all work isn't given more credence at IPCC. And the bonded all work shows that black carbon have warmed a lot. And so the warming from black carbon has pretty much offset cooling from sulfate. So the bonded all work suggests that aerosols have been not climate neutral, but pretty close to climate neutral over the modern satellite era. So, I mean, I actually read, I know this is hard to believe, only a few people here know me, but I read the 229-page paper of bonded all, and I don't see any obvious problems with it. And I don't quite understand why the IPCC AR6 is so focused on, I mean, for all I know, the people who wrote that chapter are listening to my voice right now. I don't see why it's so focused on just one paper. So that's not what an assessment's really supposed to do. So I think that there's certainly a case could be made. Okay, I'm gonna try to answer your question as best I can. Let me go back. I knew this is terrible. I think a case can be made after the bonded all paper that we should have moved from here to somewhere like here. And yet they moved here. So there we go. I'm not going to be invited to IPCC.
Maybe they'll invite you because of your comments in an optimistic world, right? Thank you. Thank you for your talk.
Yeah, I don't think being invited to IPCC is a badge of honor, particularly. We've had some good discussion. Let me try to frame a slightly different question. If you could go back to that slide, I think it's a bit later, where you had the three panels up and with different amounts of aerosol forcing. Keep going. And you're, yeah, nope, there you go. What I see in each of these panels is kind of what I would call remarkably good fit with observations. And in some ways that should be heartening, but in some ways it's kind of scary. If in fact for rather different aerosol forcings you can get this remarkable fit, then it says the fit doesn't give as much information about the aerosol forcing. And it seems to me that in some sense, by picking an aerosol forcing for each of these panels, you then are forcing the other parameters around in order to agree with the observations. Is that fair enough?
Sure. And we call this the best fit mode of our model. Fair enough.
Yeah. And so a related question would be, when one's fitting a data set, one likes to say, well, what are the number of really independent variables that you're fitting? And that one answer to that, one way of approaching that is the autocorrelation in the time series of what you're fitting. And then from that autocorrelation, you get some measure of the independence of the or the number of independent variables that number of independent observations that you have that can constrain your parameters. My question is really, how many independent observations do you have, and how many variable parameters do you have in order to get this remarkable goodness of fit?
Quick answer to Steve's question. Between 7 or 9 parameters, we talk about this in our paper. The functions go into the multiple linear regression are essentially orthogonal. So in other words, we don't have any covariance of the regressor variables, with the exception of the high frequency SAOD and volcanic aerosol. They do display a correlation. In our paper, we show a lot about the autocorrelation, the shape of the autocorrelation. So it's between like 7 or 9 degrees of freedom. Now, the reason that we can't independently pull out aerosol radioforcing better than we do is that for most of the climate record, the rise in aerosol forcing, radioforcing, and the rise in greenhouse gas forcing have pretty much paralleled each other, obviously due to the industrialization of the world. Only over the last 20 years have they diverged. So we have a very interesting set of figures in the supplemental material to Laura's paper, McBride et al., where we show the results of our model, where we stop the training at different time periods. Everything I showed today stopped in 2019. If we stop training in 1999, our uncertainties are enormous, because there, everything's going up. And the further out in time we go, the more the uncertainty narrows, despite the fact our uncertainties are still pretty large. Steve, I think that if the public health measures and the scrubbing of coal in China, and if India decides to scrub its coal, if tropospheric aerosol radioforcing truly falls as indicated by the projections, then in the next decade or so, we'll really be able to better constrain what historical aerosol radioforcing has been. This is contingent on greenhouse gases continuing to rise. Of course, I hope that's not the case. I hope the greenhouse gas radioforcing turns over as well. So the further out in time we go, the more entangled we are. Steve, we probably could have gone after this question if we had done a goodness of fit parameter over the last 20 years or so. But as you know, I think we'll see how you respond to this. I don't think that would have passed muster. Because, you know, if you restrict your goodness of fit parameter 10 or 20 years, you're dealing with all kinds of issues of climate variability. You know, there, what exactly you do with AMOC really matters. Or, so over the last 20 years, the greenhouse gas forcing has continued to warm, and the aerosol radioforcing has really leveled off, if not, gotten closer to zero. So we could look into this further, but in our book, we call this the degeneracy of the climate system. And then someone who read the book, an esteemed colleague, said I misused the word degeneracy. I don't think we did, but anyway. So we think that the existing climate system is a bit degenerate, that we just can't separate these two signals. And that's a big problem. And we wish that someone could come, Moses coming down the mountain and tell us what aerosol radioforcing really, really is. But as you all know, that's so dang hard because you have the direct effect and the indirect effect.
Well, it's kept a lot of us employed for a bunch of years. So from that perspective, the uncertainty in aerosol radioforcing is quite good. I do want to get back to pinning you down a little bit on the number of, taking autocorrelation into account and just using global mean surface temperature as the constraint on all these parameters, how many really independent observations you have and how many really independent parameters you have?
Oh, I don't quite understand the question if you talk about independent observations, because I don't even know how to answer that. I mean, I would say that every buoy that gives a ocean temperature profile is independent of another buoy. Every ship log is independent of another ship log. So for independent observations, I think it's in the millions when you talk about the bits and pieces that go in. Of course, I realize that these go into data assimilation models that minimize uncertainties and all that, but there's a huge amount of data that drives this. But in terms of the model parameters, it's basically 7 to 9.
No. What I mean is taking, maybe we discuss this offline, taking into account temporal autocorrelation in the primary data series, which is global mean surface temperature. That really reduces the number of observations dramatically, and that's kind of what I'm getting at. But if you don't have an answer to that, we can talk about it offline.
Yeah, let's go offline.
Okay, let me, those of you whose video isn't blanked out and everybody else, is a round of applause for Ross for coming in and virtually at least and giving us this very thoughtful and provocative seminar. So thank you very much.